the last thing in our notes. We're doing complex numbers, and I got a few things to fill in from what we did last time. I think the last problem was that arc length problem, am I right? Arc length problem. I'll deal with that some more. Okay, that's a great problem. So let's just work through a couple of things about the complex numbers. I saved some of the discussion. I saved some of the discussion of the magnitude for after we introduce Euler's form, because some of these little proofs are easy if you have Euler's form. Actually, Euler's equation makes all manner of things a lot easier. So once again, we have, it's the set of x plus I, y, x and y are real, and we've got this I squared equals -1 property. So we take a z equals x plus I, y, and we discover that we have all the algebraic properties we need just to do math with them. If we introduce the complex plane, then z is simply a point in the complex plane. And there would be the x, and there would be the I times y. Okay. Point in the complex plane. We can also introduce the magnitude of z. So now I've got a z. I can treat this as a vector. And I can say it has a magnitude and a direction. So the complex number could really be treated like a vector. So then we got to the actual magnitude, and what we said was we had to define the complex conjugate, where we just replace I with negative I. And then the magnitude of z was equal to the square root of z star is equal to the square root. Now you may find a mistake in the notes last time. I may have left off the square root in one of these red extra. Okay. Magnitude, and then when we had magnitude of z equals 1, then we were on unit circle in the complex plane. So this magnitude has a couple of general properties that I saved for today. And the properties of the magnitude are as follows: z greater than or equal to 0, and the magnitude equals 0 when z itself is equal to 0. The second one is that the magnitude of a product is equal to the product of the magnitudes. Now this would look a little bit complicated if you were using this form, but to prove this, and you use Euler's form, Euler's equation, it goes very, very easily. And the third property is important. It's called the triangle z1 plus z2. Triangle inequality, less than or equal to the individual magnitudes. z1 plus z2. So these abstract properties, they come into play anytime you're dealing with vector spaces. Yeah?
Did you go with the first property again?
This one here?
Yeah.
Oh yeah. So yeah, we can actually explicitly do these. So the magnitude of a complex number is always greater than or equal to 0. And the magnitude is, it's only 0 when z itself is 0. Yeah. So let's, should we try to prove these? Because when I first introduced this, we didn't have Euler's equation yet. So I'll go ahead and put that down. so we had, let's write Euler e to the I theta, where theta is real, is equal to cos theta plus I sine of theta. And that makes the connection right here of the unit circle version. So let's look at the proof of one of these. I'd say this one is self-evident by its definition up here. What about this one right here? If we were using this form, this wouldn't be fun, okay? Because you're multiplying all this stuff out. But if we use Euler's formula, let's see what we get. Proof of 2 right here. So we'll have Z1, Z2 magnitude. Remember, that's the square root of Z1, Z2, Z1, Z2 star. So yeah, we don't really want to be working with these expressions. But we can also say it is the square root of Z1 magnitude squared actually no, let's do this. Z1 magnitude e to the I theta 1 magnitude. Nope. I'm skipping steps. Better to do this. Better to do this. So this will be equivalent to Z1, Z2 magnitude squared is equal to Z1, Z2, Z1, Z2 star. Okay. I just square both sides, and then one get that equality. And so here, now we can write Z1 magnitude e to the I theta 1, Z2 magnitude e to the I theta 2. That gives us the first product here. And then we have Z1 magnitude e to the minus I theta 1, Z2 magnitude e to the minus I theta 2. That's the starred one. And look at that. Theta 1 minus theta 1, 0 gives us a 1. Theta 2 minus theta 2 again gives us a 1. Right? When we combine these here, e to the I theta 1 have e to the minus I theta 1. And so, I'll just write, e to the I theta, and then, yeah, theta 1 minus theta 1 equals 1. And so, yeah, we're just left with Z1 magnitude squared and Z2 magnitude squared. So we got that right there. Now the triangle inequality, this one I'm gonna leave for you guys. I'll start it though. Triangle inequality. I'm gonna leave these up here. This one we'll run into again when we're dealing with abstract vector spaces. And the question is, how do we prove this? And the first thing we'll do is square both sides, because that won't change the fact, because everything's positive here, square both sides. So proof of 1, 2, 3, and I'll call get started and leave you guys a couple of steps. So the first thing we're going to do, z1 plus z2 magnitude squared is going to be less than or equal to z1 squared plus 2 z1 z2 plus z2 magnitude squared. So we have to show this. We have to show this. That'll be equivalent to the one that's on the board there. And what we do is we start with the left side. So we have z1 plus z2 magnitude squared is equal to z1 plus z2 times z1 star plus z2 star. So that's by definition. And it's good to square these. You don't have to deal with the square root. And then we multiply this out, and we get z1 star, z1 star plus z2 star. Now the cross terms are interesting. Plus z1 star z2 plus z1 z2 star. Okay, plus z1 z2 star plus z1 star z2. Now these first two are easy to deal with. This is z1 squared. This is z2 squared. Okay. So really, if we look at what we have up here, we have something new to show. We have to prove that this one here is less than or equal to this one right up there. Because I already picked these off, right? I've got this and this. So I'll go ahead and write next. I'm gonna stop before I do the whole thing, okay? But next, we have to show that 2 magnitude is less than or equal to z1 star plus, no, z2 star.
We need to show that it's greater than or equal to.
Well, no, this is less than the right side,
Yes.
right?
And so by moving that to the left side, we need to flip the inequality.
No, this is still the left side. Right, this here. No,
You put the term from the left side on the right side of the equation into red. Or am I?
Oh, yeah, no, you're right, I did flip it. We don't wanna flip that, I'm gonna rewrite it. Thanks. Yeah. Very good point. So we have z1, z2 star plus z1 star z2. We have to show that that's less than or equal to the one on the circle on top. And 2 z1 z2 magnitude. Okay. So here's where an interesting point comes in here. You'll notice this is the complex conjugate of the first part here. So a number plus its complex conjugate is 2 times the real part. Okay. So this is 2 times the real part of z1 z2 star. Twos cancel. told, you know what, I said too much, but I'm gonna leave the last step to you guys anyway. It's worth it, you know, these are good review points. In fact, just making sure you recognize this is important, because we'll be doing that kind of thing a lot, you know. Number plus its complex conjugate equals 2 times the real part. And if I have Z1, Z2 star, and I do the whole star, so if I do Z1, Z2 star, complex conjugate, that's Z1 star, Z2. Okay, I gave away the game, but I don't mind. We just need practice with these. So yeah, go ahead and we'll have all 3 properties of that. So from here, I'm going to go to that homework problem. Can I erase this? Yeah. So that last homework problem is very interesting. So let's sketch it and discuss it a bit. Because it has a nice geometrical interpretation, and it involves the taking of a limit, so it's pretty rich. Okay. Let me peel this out of here. Yeah, those are these arc lengths. So this would have been the last thing in the notes from the other day. And the idea is the following. So this was that homework problem. Just see if, you know, if you have to add anything to it compared to what you already have. So the idea is we've got a bunch of equally spaced complex numbers. I'll draw this name on the plane. And since those are complex numbers, these little segments here are differences of complex numbers. So I have A, I'm tagging this with N sub K is equal to E to the I K theta over N. That's that. K equals 0, 1, 2, all the way to N. So K equals 0 is this one. K equals 1, 2, 3, 4. So this is an example for N equals 4. Okay. So here, N is equal to 4. And what we're doing is summing up the lengths of these. So L sub N is equal to the sum of all of these magnitudes, A sub K minus A sub K minus 1. So we were just dealing with the magnitudes in the previous discussion. So those are those magnitudes, K equals 1 to N. So this is A sub 1 minus A sub 0, A sub 2 minus A sub 1. And you'll notice these differences, would be the same as if these were little vectors, because essentially they are. And the proof we're going to do is that as N goes to infinity, this turns into the actual arc length. Whereas right now, it's not exactly equal to arc length. Okay. So, I'm going to give you one more step of this. Namely this A sub K to the N minus A sub K minus 1 to the N magnitude. That's just, you know, by the definition, so to speak. So I'll leave off the N, well, I'll put it there. So A sub K minus A sub K minus 1, complex number, times the same thing your definition, yeah, they, I can tag them all with the N. And when you do, you'll get something related to what I just had up on the board, and you'll have a summation of them from, you know, as n, you know, large n goes to infinity. When you do the limiting case, n goes to infinity, then you have to use either L'Hopital's or some kind of Taylor expansion in the function that you find, okay? And you'll remember that sums and differences of these, well, you'll find your cosines and stuff, okay, in there when you do this, and then the complex conjugate with the minus I and so forth. So, taking the limit and limit n goes to infinity, this else of n is then just going to be theta, the arc length theta, because we're on the unit circle. So this will be germane later on as well when we talk about integrals in the complex plane. Because in essence, this is an arc length integral, right, in the complex plane. If you, David could go to 2 pi, right, through the arc length. So this summation here is a sort of an integration. And when we do, I'm gonna just mention that right now as we go through here. These complex functions are interesting because they have a complex argument and a complex functional value. So you can no longer visualize them the way we do just, you know, f of x in the xy plane. But nonetheless, we have techniques to make sense of them. And this will get the ball rolling. So the next thing I want to do, because what we're headed for is Fourier series, but the next thing I want to talk about is the e to the z function, just in terms of what I was just mentioning here. So this is, you know, you recognize Euler's formula. So can I erase this? Do we have this? Yeah. This one's good. What was due for this week? Was this one also for this week? Did we discuss that yet?
I think that was next
This
week.
was
Yeah,
next
mine
week.
is next week.
Good. Good. So, briefly, complex functions. And what we have here is the complex plane. You know, so we just have a bunch of z's here. But what is a complex function f of z? Here's, you see the argument is x and y, and if we had a one variable function, then it would, you know, we could do this. We could say, yeah, that would be the complex plane, and then, you know, the way we do multivariable calculus, and that would be, you know, a hill, a valley, or what have you. But we can't do that because this f of z is itself a complex number. So what we have instead of a function that you can visualize there is a mapping. In other words, every point here gets mapped over into the complex plane. You no longer can just visualize them, but you can visualize aspects of them. Okay. So the most important example here is f of z is equal to e to the z. Complex exponential. So we do have some examples of this. If z is equal to x, real number, yeah, then good. Then we have the x-axis, e to the x function that we know very well. And if z equals I times y, then, well, then what? Then actually, I'm not gonna try to graph it. If z equals I times y, we have something that we can deal with very nicely, and we can have f of y if we want. I'll write it this way. F of z, give it a new name, f of y, since we're only using one of those, equals e to the iy. And then we have Euler's formula, okay? But we're already no longer able to graph it one axis to another axis, okay? So we can't graph it as a function, but we know this thing very well. This is our cos y plus I sine of y. So what we're going to do in the next section is just work with complex functions of one real variable, okay? What we do after we've learned that and done quite a bit of stuff, we actually do what's called theory of functions. That's complex functions in the complex plane. And in that case, you know, you can do, say, an integral, and you'll start doing an integral, you know, contour integral it's called, and you won't be able to visualize the same way we visualize functions. So we won't be able to just visualize it this way, but we'll have methods of dealing with that. Good. So I hope I didn't spread any fog here in the, yeah.
Well, just a practical query, what do this math be used for?
Everything. This is the foundation. So we're gonna start using it for Fourier expansions, trigonometric expansions, and that's gonna be the next big section. And then, a lot of physics just happens in the complex plane, actually. So one of our practical things will be, once we actually launch into the complex plane, it'll give us powerful techniques for solving ordinary integrals that we can't otherwise solve. So yeah, this is one of the greatest chapters in all of math. In fact, if you take a full semester of complex analysis in the math department, it's actually highly recommended just to get more, but we're gonna get a fair amount of that. So without further ado, we're gonna work a lot with this one here, okay? And that's what I'm gonna illustrate now. Yeah, oh, there's just an enormous amount of, anybody ever done Fourier series? You probably have, yeah, anybody else? Yeah? Okay, was I exaggerating? It depends if you've done the real ones or the complex ones, but yeah, we're gonna do the whole thing in a couple different ways. So without further ado, we're going to use the Euler's equation, which is the simplest, cleanest introduction to trigonometric series. Okay. So this chapter is Fourier series. And I'll put here trigonometric series. And we can motivate them. Trigonometric series. We can motivate them with the idea that we already have Taylor series, right? So first, if we have Taylor, we have, you know, f of x equals an infinite series of, you know, your kth derivatives. So it's a power series. K equals 0 to infinity, x minus x naught to the kth power. So that would be the Taylor series. And if we expand around 0, then it's just, you know, power series of x explicitly. So what if we tried this? F of x is the sum of a sub k cosine of kx. Since we know that cosine, and we could have sines as well, okay? We know that the cosine itself has a power series, so this might be a really complicated sum. I'm not going to specify which ones, k's or integers. right? We know this itself is a power series, so we could say this is reducing to some power series in a complicated way. But over here, we'll do a little graph for x0 equals 0. Remember, this is a combination of straight lines, parabolas, cubics, etc., right? And what would this be a combination of? Cosines, and then of higher and higher frequency cosines. Okay. No point in trying to draw that anymore, but you get the idea, right? That's what these are comprised of. Okay. So it turns out that the real version is best approached from the complex numbers. Okay. And that's what I'm going to do here. Suppose f of x equals the sum k equals minus infinity plus infinity c sub k e to the I k x for minus pi less than or equal to x less than or equal to pi. Okay. That interval. Then what would be going on here? We'd have cosines and sines, we'd have a bunch of imaginary parts, real parts, right? We have a whole giant expression, but we know that buried in here are the sines and the cosines, okay? And that's why we have to be confident with the use of Euler's formula, Euler's equation. So suppose a function, and now I'll draw it here. Suppose a function minus pi to pi can be expressed like this. There's such a function. The question then is, what are the coefficients? What are the coefficients? C sub k equal to, supposing that's possible to do. So that's the big question here. We know that the sine, cosine, real, imaginary, all kinds of stuff is buried in there. But, and by the way, suppose this is a real function now. It's a real function, one I can draw with a pencil. And is it possible to get a set of coefficients where this will add up to that? And the answer is it is possible. And I'll just construct them right here. So we're going to look for the coefficients c sub k that make this sum. And the convergence criteria we'll talk about later. Convergence criteria for these things are similar but a little different. So we're just going to diagonally say good at all convergence. This combination here delivers me that line. Okay, so here's what we do. We're going to take the same equation but leave some space in. Okay, leave some space here. Sum over c sub k to the I kx. I'll just write k there. And we're going to multiply it by e to the minus I n x minus I n x, and we're going to integrate it from minus pi to pi over dx. So integral minus pi pi dx. So we have to work on the right side here. And we're just going to assume these sums are sufficiently well behaved that we can exchange the integration and the summation. So we end up with a summation of c sub k integral minus pi to pi e to the I k x. You know what, I'm going to just leave yourself some room. E to the I k minus n x dx. Make sure everybody sees that step, because this is quickly done and pretty important. Okay. So what I did was I just exchanged integration and summation. For a finite sum, you could always do it. So we could also think this went up to some finite n if we needed to. Okay. And e to the I kx, have e to the minus I n x, right? If you use this property of the exponential, k minus nx. Well, this here is actually really nice. This integral here, if k is equal to n, what is this integral equal to? The one in the bracket. K equals n. Yeah, e to the I times 0 is 1, and therefore I have a 1 dx minus pi to pi. So integral equals 2 pi, and if k is not equal to n, then we have to look at this, and we'll find that the integral is equal to 0. So I'll prove that next statement just to make sure it's not in doubt. So here we go. We have integral e to the I k minus nx dx. K is not equal to n, so we can deal with this very nicely. 1 over I k minus n e to the I k minus nx minus pi to pi. So what's e to the I times an integer times pi? Versus e to the I times an integer times minus pi. It's the same thing. A couple ways to see this. If you're living here on the unit circle, you know, you're going around k minus n times pi in one direction versus k minus n times pi in the other direction. That's one way to look at it. You land on the same point. So that difference, that really is 0. And so we now have something very nice. Everything here is 0 except for when k is equal to n. So what we found is integral minus pi to pi f of x dx is equal to the sum over c sub k and then times 2 pi. And I'm just going to introduce the Kronecker delta right here because we got to know it. Times this function called Kronecker delta. Oh, I missed something. What's more with the feeling? A little farther to the left here. Pi to pi f of x e to the minus I n x dx. Okay, there we go. Summing over k, Kronecker delta k n. So now's the time just to introduce that thing. Does everybody not know the Kronecker delta? Delta k n equals Kronecker, that's the name of a mathematician, delta, and it's defined very simply. It's equal to 1 if k equals n, 0 if k is not equal to n. So that's exactly what we had here. You know, we have 2 pi times a 1 if k is equal to n, 2 times 2 pi, 0 if k is not equal to n. So how do we evaluate this sum here? We've got an infinite sum. So but only one of these values is a one, so we end up with C sub n times two pi. And this answers the question that we originally asked, what the value of the C sub n is, or the C sub k. I can use k again if we want. I'm gonna start over here. So answering that question, we have C sub k is equal to 1 divided by 2 pi minus pi of pi f of x e to the minus I kx dx. So I just substituted n for k again, which I was all done. What I had here was C sub n and divided by 2 pi. And we call it C sub k again, it was n. So that's answering the original question. So this is a really stereotypical move. And we'll see that later in the generalized algebra. You're multiplying something with a function and doing an integration. This will actually turn out to be a scalar product when we get there. Right now, it's just the recipe for finding the Fourier coefficients. Okay. So yeah, this calculation you should look at a couple times. You'll see it again in many forms. In E and M and stuff, when you have different special functions, they won't always be as simple as the complex exponentials, but it'll be the same move again and again. Like you take quantum mechanics, you see this all the time. Good, so you saw it here first. Let's, okay, I'm gonna erase all this and I'll just formulate what we found, right? So we can just look at that. I'm sorry?
Even comes up with thermodynamics.
Yeah. Orthogonal functions?
Yeah.
Yeah. So yeah, we're gonna do that. So, okay, so trigonometric series. Now the thing is, the complex ones that we just did are the simplest to prove. You need to know the complex and the real form. So we're actually gonna get a whole slew of formulas going, but first we'll do an example. Okay. And the example I do goes beyond what Taylor expansions can even do. Okay. So the example that we want to calculate is, suppose we want to expand the step function in a series. We can't expand a step function in the Taylor series. The step function is going to be 1 for 0 less than x less than pi, and -1 for negative pi less than x less than 0. And if you draw this thing, this is what it looks like. You've got pi and negative pi. And down here, you've got -1. And here you've got +1. You've got nothing at the origin. Okay. So try expanding that into Taylor series. You don't even have a single derivative, let alone infinite derivatives, right, at the origin. And yet this is very easy to do with a trigonometric series. I'll kind of give the game away. What's going to happen is you're going to have something that does this, except you're not going to see the waviness. And it actually, the result we get goes through the origin. And, that is up there. But we have to do that step by step. See if I think we can do that today. So here's what we have. We have C sub k, and again, minus infinity to plus infinity, e to the I kx. Whole huge sum of these. And let's write this out briefly so we can kind of see what's going on. We're going to have a C sub 0, okay? Then we're going to have C sub -1 e to the minus I, or I could do it in the other order. But this is how they come up. They come up in pairs. So c sub 1 e to the I x plus c sub negative 1 e to the minus I x plus c sub 2 e to the I 2x c sub negative 2 e to the minus I 2x. Right? You can see that kind of building in that form. Because yeah, this thing here. With c sub k equal 1 over 2 pi, f of x e to the minus I kx dx. So the first thing we see, what's c sub 0 going to be equal to? C sub 0. We plug a 0 in here. We're integrating f of x from minus pi to pi. What's the answer?
It's not a function, it's a zero.
It's 0. It's an odd function, right? We're getting minus pi u plus pi there. Boom. It's equal to 0. So c sub 0 is equal to 0. Odd function and all. But now c sub k in general, so k not equal to 0. Here's another interesting thing. C sub negative k equals 1 over 2 pi. This is still the general definition. F of x e to the minus I negative k x dx. You'll notice this is equivalent to just replacing the I with a minus I, right? That being the case, we can say that c sub negative k is equal to c sub k complex conjugate. That's just a general fact, because this then is e to the I kx, and we've replaced I with negative I, which is the complex conjugated thing. So now we actually have to get to work and do the integral. So we'll do 1 over 2 pi, and this is a sport where you can lose minus signs pretty easily. So we're going to break this function up into minus pi to 0, and then we have negative 1 e to the minus I kx dx, and then we have 1 over 2 pi, 0 to pi. So I just use the additive property of the integrals. And here I have positive 1 e to the minus I kx dx. So let's see, what we get for the first integral, we've got minus 1 over 2 pi. Then we have 1 over negative I k e to the I kx e to the minus I kx from minus pi to 0. We have plus 1 over 2 pi. Well, plus 1 there. 1 over negative I k e to the negative I kx from 0 to pi. So these have to be evaluated. And the integrals we just did, pulled 1/2 out. Remember, e to the some number times x, 1 over that number, e to the same thing x, minus pi to 0. So this should be good. And these signs will cancel, so I'm going to have 1 over 2 pi I k, 1 minus e to the I k pi. Right, e to the 0 is 1 minus e to the minus negative pi, right, so plus I k pi. So if we just clean this thing up. And we need a little more room over here, so let's just have a shot. See how far we get. So what do we have here? We have C sub K equals, I can do the 1/2 pi I K. And, I'm gonna pull this minus sign out. So I will have 2 of the same thing. Okay. 2 minus e to the I K pi plus e to the minus I K pi. I can even factor a 2 out, 1 minus, factor a 2 out, 2 over 2 cosine I K pi. Okay. So when is the, oh, not the I comes out now, cosine K pi, right? So that step there is important. That was 2 cosine K times pi we've been looking at. And so when is this cosine 0 or 1, and when is it -1? So when K is equal to 0, 2, etc., it's equal to 1. When it's equal to 1, we get a 0 here. So this thing equals 0 for K equals 0, plus minus 2, plus minus 4, etc. And what is it equal to when K is equal to, see, 1 minus -1, right? So it's going to be equal to 2 for K equals plus or minus 1, plus or minus 2, plus minus 3, etc. So now we have to put this thing together again. We have to reassemble the thing.
How can it equal 0 and 2 for positive -2? You have to have.
Oh,
both
sorry,
these.
3. These were the odds. These were the, sorry, missed that. These were the odds. Plus 1 is -1, plus minus 3, plus minus 5, yeah. So evens, odds, yeah. And so now we can actually plug in so it equals 4 over 2 pi I K for the moment. When K equals plus minus 1, plus minus 3, plus minus 5. So if we can do it just for plus minus 1, we'll be in shape, okay, for the entire infinite series. So here we go. So we have this f of x equals the c sub 0 is a 0, c sub 1 plus c sub -1. So 2 over pi I ix plus 2 over pi I, because k is equal to -1, so minus e to the minus ix form, we're gonna have 2 over pi, and then I'm going to do 2 over 2i for this 1 over I, e to the ix minus e to the negative ix. And here we go. We get 4 over pi. And what is this? E to the ix minus e to the minus ix over 2i. That's the sign. So 4 over pi sine of x. And now if we just put those k's in there, we'll be all set. Okay, so that was for k equals 1, and we have plus and so on. So for k equals 3, 5, etc., we're going to have the following. So we're going to have 4 over pi sine of x plus 4 over 3 pi sine of 3x plus 4 over 5 pi sine of 5x plus and so on. Odd powers, oh, there's an x here. That one was not k, that was x. Okay. So we could put this in closed form if we wanted to. We'd have to express the 1, 3, 5 in terms of some k's there. But this will actually be enough. We have a minute or two yet. So we're going to put this in closed form. I'll write f of x right here. We're going to put this in closed form later. Everybody see the pattern? Sine of kx over 3k, over k pi for k odd, 1, 3, 5, 7, 9. Okay. So this is an odd function. And once we go ahead and draw our picture, we'll have something. I'm not going to assign anything because we have something for the weekend anyway. So what would this picture look like if we just took the first term, 4 over pi sine of x? I'm going to go plus pi minus pi. So what's 4 over pi? 4 divided by 3.1, it's a little bit more than 1. So if we have a 1 here, then we're a bit more than the 1. I'll draw a dotted line, negative 1, a bit less than the negative 1. And since that's just the sine of x, so the first term here goes like this. Not yet looking like a step function. Okay. But now we're going to add 4 over 3 pi, so we go to 1/3 this height, which is about here. And since it's the sine of 3x, we're going to get 3 of these. And the other ones I'm going to have you guys do on a machine. So we're adding this plus this plus this. And what happens if I add the red and the black lines? I'm not even going to try the 5. Let me get another color here. The 5 is beyond the Call of Duty, but here's another color. See if this writes. It'll work, yeah. Okay. So if we add these up, you'll notice we're adding a positive and a little negative, so it's going to go through there at that point. Here we're adding things that make this steeper, so it gets steeper, adding this and this. So roughly speaking, it's gonna go up like that. Okay. Now, if you add the next one, and the next one, and the next one, eventually get it steeper and do that till you can't even see, that. Now, has anybody ever used a function generator in the lab? Step functions, sawtooth functions, or anything? No? Haven't done that yet? Physics?
On the
4B lab? Or is it in optics, or what do they do? Oscilloscope, yeah.
Yeah.
Function generator, oscilloscope.
I've done it in intro to engineering back in community college.
Oh, yeah. That's how those functions are created. So a function generator creates a step function. If you zoom in enough on it in the oscilloscope, you'll actually see some of this structure, because they don't go out to infinity. So yeah, that's how these things can be synthesized. So you can synthesize using these functions a step function, and what we'll do next week on the homework, like maybe the first homework problem, or one of them will be to do this function here, which will also have a function generator, the sawtooth function. Or actually, that's a zigzag. A sawtooth is one that goes up like this. And those can all be done with Fourier series, okay? So we have some really nice applications. But for now, we'll just leave it at this. I think we'll start with this, and then we'll write down the closed form and do some other stuff and kind of review this. Good. So that gives us 5 minutes. We'll lead ahead on down and get that number from Megan.